Friends, welcome back to the series on statistics and probability, especially probability. You start with probability and try to be as clear as possible about the concepts, because as we will see, many professionals make mistakes. Why? Lack of clarity of mind, lack of understanding of the core concepts. So let's start with the mother of all problems, fat tails. Or more scientifically, it's called thick tails. Fat tails being a special case of very, very thick tails. But, casually we can call them fat tails. So, what are fat tails? Whenever I ask people, they tend to answer, remote events of big impact, tend to happen more often. No, it's the opposite. Remote events happen less often, but when they happen, they command much greater effect on the total properties.
Okay, so here we will see that this really depends on the definition of extreme or remote events, but we will see this later.
So the definition of fat tail is the smallest number of observations in a given data set will represent the bulk of statistical properties.
Okay, so what does Professor Taleb mean by this? So Professor Taleb is introducing his definition of fat tails. Usually in the literature, as we have purposefully defined previously, fat tails are usually defined in terms of the speed at which probability density goes to zero at infinity. Otherwise, they might be defined in terms of a kurtosis, which is a measure that given a probability density, you can compute this measure. And you can say things, you can define fat tails in terms of this measure called the kurtosis. Taleb proposes his definition that is very useful in applications. It has an applied scent to it. And his definition is going to be in terms of a rate of convergence of a law of large numbers. Specifically, he defines this metric, the K metric, and this will be the metric that is a proxy for how fat-tailed a distribution is. Or actually better, the K metric, the fat-tailedness of a distribution is going to be defined in terms of this K metric. And this K metric is determined by changes in, by the rate of convergence of the law of large numbers. So what is the law of large numbers? The law of large numbers is a theorem in statistics. It's a true fact that says that the sample mean of a certain probability density as the observations go to infinity. If you compute the sample mean of these observations as it goes to infinity, then the sample mean will converge, as the number of observations goes to infinity, it will converge to the true mean. The sample mean converges to the true mean under some assumptions. Now, this is a beautiful fact, one of the main theorems of statistics. And how come you can think about defining fat tails through the rate of convergence of the law of large numbers? Well, an intuitive reason why this makes sense is that the speed of convergence of the law of large numbers does depend on the variance of the distribution through which you're sampling your observations x1, xn. And so, as we have seen before, a heuristic for fat tails is the fact that the standard deviation, which is thus the square root of the variance is the standard deviation squared. And as we have seen before, heuristic for fat tails is that the ratio of a standard deviation over the mean absolute deviation is high. So of course, if the standard deviation is high, this ratio is going to be higher. This should be an intuitive reason why one can define fat tails this way. Another reason you might think that in a with a fat tail distribution, your observations are not going to be as precise as a thin tail distribution, and so the sample mean is gonna have more variance than the sample mean of a thin tail distribution. And so this should make some sense intuitively. Now, we're not going to talk much more about the law of large numbers because we're going to see it in detail in further mini lessons. I just wanted to explain what Taleb meant when he said the smallest number of observations will represent the bulk of the statistical properties. Now, if you read his book, you understand that this translates to how much will additional data help increase the stability of the observed mean. With the bulk of the statistical properties, Taleb means the sample mean and the sample quantities derived from the sample mean, so the sample standard deviation, etc. These are the bulk of the statistical properties. And he defines fat tailness through this K metric. So I'm just explaining this phrase, unpacking the phrase Taleb uttered.
So let's take a case of an extreme fat tail process. You remember we had 1,000,000 minus 1 observation as 0. And then we had 1 observation at 1,000,000. What is the average? 1. But most of it, all of it, came from 1 observation. That's fat tails. You sample from the population of the planet. You got 3-4 billion people who have no money. You add Bill Gates randomly of the people on your hero list. Jeff Bezos, Warren Buffett, either one of them, one, you'd be the entire wealth plus noise. You have a little bit of noise here, so that's a fat tail process.
Okay, so with this little toy example, this little toy probability distribution, we have 1,000,000 possible outcomes. 1,000,000 minus 1 of them are going to be zeros, and the last one is going to be equal to 1,000,000, and they're all going to be equiprobable with 1 chance in 1,000,000 of happening. So this little toy probability distribution we have just defined, Taleb says can be used, for example, to model if we pick person randomly on Earth and we observe the amount of wealth they have, well, then this distribution can be used to model that data generating process. The data generating process of picking people at random and seeing how wealthy they are. Why is this the case? Because most of us, you and I, have approximately 0 wealth. And then there's a few people who hold all of the wealth, who have a great deal of wealth. So if you would like to measure this certain data generating process, this certain phenomena of wealth distribution, this might be a good probability distribution to do so. Now, this is the main reason Taleb brings up this toy example is because it expresses a case of a fat tail distribution where the extreme observations are going to be very rare. There's only going to be 1 chance in 1,000,000 you see this big fat guy here, the 1,000,000 chance happening. I shouldn't say fat, this bulky guy here. So extreme observations are going to be very rare, but when they happen, they are massive. And this is a bit counterintuitive, because when you think about distributions with fatter tails, you might think that the extreme observations happen more often. But this is not the case, and it really depends on the definition that you're going to give of extreme observations. In this case, we don't have much choice because the observations are going to be either 0 or 1,000,000. So the extreme observation is, of course, going to be 1,000,000. The definition of extreme is going to be the observations that return 1,000,000. And so in this case, extreme observations are going to be rare, which for some might be counterintuitive. Okay, so this firstly introduces this fact. And then lastly, let me just say that we can understand why this distribution has fat-tailed, other than the fact that its variance is very high, through the definition, through the K metric. So intuitively, let's say we have a sample of 10,000 observations from this toy example distribution. Well, then it's going to be pretty likely that these 10,000 observations are all going to be 0. And so the sample mean is going to be 0. So it's not going to be 1. If with 10,000 observations you haven't moved an inch towards the true mean, well, that intuitively resembles a slow convergence rate. Now, otherwise, you can see it the other way. Say you're lucky, quote unquote, and you see the extreme observation, the 1,000,000 observation, as your first observation. Well, then you're going to need a large number of other observations to bring the mean down to 1, the sample mean down to 1. So, as you can see in both of these cases I've described, intuitively the sample mean seems to converge very slowly to 1. So this is just some intuitive notions to try to help you understand or see why this toy example is fat-tailed, even though we've seen it before. Now let's see what else Taleb has to say to us.
Now let me try to get more technical, a little more, but not really technical. And let's take a probability distribution. This is the Gaussian probability distribution. 1 sigma minus 1 sigma. We know that about 15.6% of observations happen beyond 1 sigma. So usually I quiz people, I tell them what happens when you fatten the tails of the Gaussian. What happened in that corridor? 67.8% of observation is supposed to take place here. What happens? Before I wrote my book, answer, typically, well, fewer observation here and more here. No. You have more observation here and fewer observation in the tail, beyond 1 sigma. Because the event that will happen there, the deviations will be fewer above 1 sigma, but when they happen, boy, they're going to be important. So that's the definition of fat tail. And this is where, mistakes tend to be made in interpretation. The central thing about fat.
Okay, so here, the important thing to understand is that Taleb has a personal and beautiful and elegant way to fatten the tails of a Gaussian. So when he says if we fatten the tail of a Gaussian, this and this will happen, he has in mind a very specific way of doing it. This way of doing it is by, as he says, adding a second layer of stochasticity to the Gaussian distribution. What this means is that the Gaussian distribution is defined through 2 parameters, the mean and sigma, and these are real numbers. And one can think about rendering the standard deviation stochastic itself, so assigning a probability density to the standard deviation. Now, if one does this, then he will obtain, he will construct a density that has fat tails. This is quite elegant because you're taking a density and then which represents something stochastic, and then you are thinking about the parameters that define this density stochastically themselves. So for a very simple way to make sigma itself stochastic, we can assume that sigma takes only two outcomes, 1 minus a and 1 plus a, where a is some real number. And these outcomes are both have both probability 1/2 of happening. So this is a very simple way of making the standard deviation of a Gaussian stochastic. And then if we do this, we can compute the probability density of x, which initially we are taken as distributed as a Gaussian. Well, then we can compute it through the law of total probability, and then Bayes' rule, and we can see that we obtain this kind of average of two Gaussian densities with different standard deviations. Now, this is the specific way Professor Taleb fattens a Gaussian. With this specific way, the figure that's going to appear is going to be something like this. Here in light green, you see the fattened version of a Gaussian distribution. Here in dark blue or black, you see a Gaussian distribution. And this in light green is the fattened version of a Gaussian with Taleb's nice way of fattening. As you can see, as we can expect, after a while, the fattened distribution is gonna dominate the Gaussian. But very importantly, for what Taleb says in the video, you can see here that there's going to be a peak where the fattened distribution dominates the Gaussian distribution around the mean. So observations around the mean are going to be more likely to appear for the fattened distribution than from the Gaussian, if you fatten something like this. Now, why would you want to fatten distributions like this? Well, firstly, as you have seen, it's very pleasing mathematically, but then secondly, some data generation processes might actually follow this kind of light green density. So one can do this, but it makes sense to fatten a Gaussian this way. But of course, this is not the only way one can think about fattening a Gaussian. One can think about fattening a Gaussian by just pushing down the center of a Gaussian. And here in light blue, you see the Gaussian distribution, and here you can see that if you push down the center, you obtain this kind of fat tail distribution in yellow, orange, whatever this color is. In this case, you don't get the slightly counterintuitive fact that around the mean there's going to be a higher likelihood to see observations of the fat tail distribution than the normal one. While here you do see this. And what else do you see? Well, you see that there's a peak around the mean where a fat tail distribution will have greater density than the Gaussian. This is what we were just talking about, this region here. Then we see that we have these shoulder regions that go from A3 to A4, where it will be the Gaussian distribution that dominates the fatter-tailed distribution. And then in the tail region, as we already said at the start, the fatter tail distribution is going to dominate the Gaussian. What does this lead to? This leads to the fact that if you define extreme observations as one that are one standard deviation away from the mean, then the Gaussian is going to have more, the probability of seeing extreme observations is going to be more for the Gaussian than for the distribution with fatter tails. Why, intuitively, can this be the case? Because of this peak here, you see? Here, it's more likely to see observations that are in this region for the fatter tail distribution. So even if we expand this region a bit towards the shoulders, it is still going to be the case that we're going to see more observations in this expanded region for the fatter tail distribution than the Gaussian. Now, crucially, this depends on the definition of extreme events. If we were to define extreme events as events, let's say, that happened after the number 4 here in the tails, then we would get back our intuitive understanding of at least the more natural way that probably most people think about it. That is that the distribution with fatter tails will have a higher chance to see extreme events. If we define extreme events this way, higher than 4. So in this way, the Gaussian is going to have a less likelihood to see extreme events than the fatter tail distribution. But the takeaway here is just that when you fatten a distribution, things are not always going to be so intuitive as you expect them to be. The takeaway is that there are ways to fatten a probability distribution where if you define extreme events in a certain way, you're going to see less extreme events happening for the fatter tail distribution. Now, crucially, this depends on the definition of extreme events. Okay, I think I've explained this enough. It should be clear now. If you can repeat, you can just watch the video back again. Hopefully it's clear. Hopefully.
Tails, and we'll see that progressively throughout the series. That people say, oh yeah, we know the markets are fat tail. Oh, we know economic life is fat tail. If you knew it, you wouldn't be writing the papers. If you knew it, you would not be using concept like standard deviation. If you knew it, you wouldn't be using variance. You wouldn't be using correlation. Like in IQ studies, they correlate IQ, which is thin-tailed, by construction, by the way. Okay, Gaussian. Sort of thin-tailed. To income, fat-tailed. You can't. Can you do regressions when you have fat tails? No. Why? Something called the Gauss-Markov theorem. It's an assumption. It's supposed to hold. Otherwise, you don't have regression. So a lot of things go out the window under fat tails.
Now, this is the main point of a lot of Taleb's work. So just let me explain this. In practice, we know, scientists know, and people who work in academia know that some data-generating processes, some natural phenomenons are not fin-tailed. So we know this because we see data that doesn't really seem to belong to a fin-tailed distribution. So there are many data-generating processes that are fat-tailed. Yet, a lot of them are modeled through the Gaussian. Why? Because the Gaussian allows you to make sweet models, nice calculations, and make statistical tests, etc. And it allows you to publish papers too, because you have made a model of nature in some way. The problem is that if you use a fin-tail distribution to model a data-generating process that has fat tails, a lot of things kind of go out of the window. So first of all, your sample mean is not going to be close to the true mean. For it to be close to the true mean, you're going to need trillions and trillions of observations in some cases. So in many cases, your sample mean is going to converge so slowly to the true mean that if you only have 10,000 observations or a human level of observations, you're going to remain, your sample mean is not going to mean much. And if your sample mean doesn't mean much, then your sample standard deviation, that is defined in terms of a sample mean, is not going to mean much. And if your sample standard deviation is not going to mean much, then your sample correlation, that is defined in terms of a sample standard deviation, is not going to mean much. So all these statistical measures that we compute on our data are going to lose a lot of their informative power. They're going to be uninformative. Now, along with this fact, then there's a number of consequences. I think there's 17. Here I just took a screenshot of Taleb's book that you can find for free online on fat tails, the consequences of fat tails. And so for example, as Taleb was saying, regressions, even regressions don't work if you don't have normality assumptions. Anyway, he's going to talk about these things more in further lectures, so in further mini lessons, so we can talk about these things when we reach them.
For now, for the next few presentations, we're going to be intuitive, break down concepts, maximum clarity, because what these professionals who make these mistakes, what they share in common is that their mind has a clarity of a New York sewer the day after Thanksgiving. So you can imagine the clarity of mind of professors. So they don't get it. I mean, they have so much junk in their head that they don't get the essential. That if you accept that it's fat-tailed, then regression, all these things have absolutely no information. No, they're not informative, to use the technical word. You got to do something else. And of course, we can do science, more rigorous science, but it requires some effort. Great. So for now, thank you very much and have an excellent weekend. Bye.